Hey everyone. As you can probably tell, I'm not Julian. He was gracious enough to swap spots with me due to a scheduling conflict on mine, but I'm here to talk about account abstraction with Polygon Miden. What I'm going to talk about is basically how account abstractions work in Polygon Miden. I'm not going to kind of sell why we need account abstractions. I think the talks and panels before that have done a good job of that, and I think the other talks to follow will probably complement this. But I want to kind of provide a different way, because we talked about how account abstractions work in Ethereum, and there are some other native account abstractions like in Starknet as well as in Aztec, but Polygon Miden actually offers a very, very different model to that. So like, I wanted to show what else is possible or how else we can look at account abstractions. Before getting to actually how it works in Miden, I want to show how like we can think about different ways to execute smart contracts. Or like transactions in general. So like you can think about sequential execution. This is, for example, what is done on EVM. Users send transactions into to the block producer, to the network, and then the block producer puts them in a sequence, executes one after another. You can also have parallel executions. There are some chains that do that. Also, like on EVM, you can do parallel execution with block STM type of things. But we can push this one step further, and we can actually say we can execute things on the client side. So like instead of the block producer executing the transactions, the clients themselves execute the transactions, generate proofs that the transactions were executed correctly, and send the proofs to the network. And then the network just verifies that the proofs have been done correctly. This cannot be done like that easily. You actually need a different state model for this. Like you cannot kind of deploy it on a let's say EVM-based state model. That would be very difficult, or at least I don't know how to do it. So a big part of how Miden works is like redefining the state model and what it means to execute a transaction. So I'm going to go through that. So at the heart of Miden design is what we call an actor model. This is a very kind of known model of doing concurrent computations in distributed systems. So you can think about actors as like the state machines with inboxes, and the way they communicate with each other is by sending messages. And the messages are produced by actors and consumed asynchronously, and the message basically can affect changes on an actor. It can change its state. It could ask an actor to generate another message, things like that. So in Miden, you have a concept of accounts, and it's actually a combination. So it's a combination of account-based and UTXO-based model. So you have accounts. And accounts maintain their own state, so that means like storage. Every account has storage, and they also maintain a set of interfaces that they expose. And the way they communicate with each other, they produce these nodes, which carry assets, and they also have this spend conditions scripts that you need to execute to consume a node. And then so a simple transfer in Miden, for example, would actually take two transactions. The first transaction would take assets from the account, put it in a node, put some spend conditions on that node, and then it would the node would be recorded on chain. And then the second transaction would consume a node and move assets from that node into an account. And the important thing is that you can think of like you updating the state of one account has nothing to do with updating the state of another account. When you move money from one account to another, you make two updates independently. And this is what allows you to prove the state transitions independently. Like on Ethereum, for example, this would be, you update state of account 1 and 2 at the same time in a single transaction. And therefore, if somebody tries to like move money from like multiple sources, like there would be a conflict. You can't do that. But when you separate the state transitions and only involve one account in the transition, you can actually prove the execution separately. So let's go a little bit more. So like an account on Miden, has an ID, has nonce like on Ethereum, but every account is a smart contract. So this is like what we talk about when we talk about account abstractions. And so like it has code. Every account has code. And I'll talk in a bit more detail like what exactly this code implies. It also has storage. And one other important feature that makes this state model possible is that assets are stored locally in the account itself. So like when you move asset A from an account to asset B, you don't need to update some global ERC20 map. Like an account is actually like there's native assets which are stored locally in each account. So like again, you don't need to update other states. It's like very important to minimize the amount of shared state that you need to manage, because anytime you need to have shared state, you can't like do local proving. You have to have network execute the proofs or execute the transactions to generate the proofs. So yeah, so that's what I said. And then we have like two types of assets. It's fungible and non-fungible assets. Nodes, also to go through this a little bit. So we have scripts that define the spend conditions for the nodes. The scripts are super flexible. You can put anything in there. You can say, for example, who is to receive this node. And you can specify based on account ID or a signature or whatever else you want. You can actually make the node consumable by any number of accounts, and whoever consumes it first can take and executes the conditions of that node, can basically grab the assets in the node. And this could be used, for example, for atomic swaps. You basically can consume a node that says, if you consume this node, you have to produce a different node with a different asset that goes back. And so you can have an atomic swap done using this node mechanism. You have some inputs. This is kind of basically data associated with the node. You have a serial number that is used for privacy. Basically, you want to make sure that all the nodes are unique to generate like unique nullifiers and all of that. So I'm not going into this now here. We have ability to actually hide the transaction graph. So we're privacy preserving protocol, the nullifier allows us to make sure that there is no linkability in between which node gets consumed and which nodes gets produced. And then nodes, same as accounts, have assets in them, so they carry assets exactly in a node. It's a container of assets. So again, there is no need to update any kind of global maps or anything of that sort when you move assets from account to a node or from a node to an account. All right, so a transaction in Miden, just kind of tying these things together, is really a state transition of a single account. A transaction never updates more than one account at a time. Then this is, again, why you can do it locally in most cases. You can read other account states, so you can actually read other accounts, you just can't update them. And a transaction can consume 0 more nodes, and it can produce 0 more nodes. So like you can imagine kind of the way accounts interact with each other is by sending nodes, like the trigger changes in a different account, and then another account can generate a node as a result of that, and that account can go to a different account, and that's kind of cascading set of calls. So you can think of these actors like communicating with each other asynchronously. And here I want to show like a simple, like this is an example execution. So let's say we want to have a transaction that consumes 2 nodes and applies these nodes to a single account. And the transaction consists of a number of different steps, but the first one is there is a prologue that like does some bookkeeping things. For example, it sums up all the assets that go into a transaction, and then in the epilogue section we'll verify that no new assets have been created or destroyed during the transaction. So you would have kind of the consistency, like this is enforced by the network that you can't, except for special cases when you need to create new assets. In most transactions you are not allowed to create new assets or destroy existing assets. And then the execution step is like, it's going to call execute on the node script. And the node script is going to call some interface method on the account. And this interface method would perform whatever is defined in the account. So in this case, it could say receive and pass assets that it has in the node into this account. And then account is going to do some work based on that. They can modify its own state, they can create new nodes, they can do a bunch of things, but it is defined within the account what this interface method will do, and then it returns. And then execution proceeds to the next state, to the next node, and then let's say the node is exactly the same. But it could be also a different node, it could do something else. In this case, for simplicity, I use the same exact method. And so you get this kind of flow where nodes execute, nodes invoke methods on the account, and then some effects happen of that. The user needs to sequence which nodes are executed first, which nodes are executed after, but like once you specify what you want to execute, you kind of like, you can say, I'm consuming this set of nodes in this transaction, they can update my account, and therefore the transaction is going to result in this. So the other thing that we have in Miden is what we call account components. And this is the way we define the actual kind of the state of the account. And this is like a very interesting and also very different approach. So By itself, an account is empty. It doesn't have any methods. It doesn't have any code. It doesn't have any storage. It doesn't contain anything. But you can, for example, deploy a wallet interface. And this wallet interface, like receive function, would be part of the wallet interface. Like there would be a send function that is part of the wallet interface. And if you don't deploy this wallet interface, for example, you won't be able to send the receive assets. You can also have different wallet interfaces. I'll talk about it in a second. But this is one of the things you can do. You can separately deploy a different component, which could be your authentication mechanism. So you can specify how you want to authenticate transactions. And this could be, using a CDSA signature. It could be some, post-quantum signature. It could be multisig. And you could actually compose different things in there in a way that, for example, you want to say, I'm going to deploy two different keys, two different authentication components into the account. One authentication component is rate limited. It can only spend like 10% of the balance of a given asset in a given amount of time. And the other component, authentication component is not limited. If you have that key, you can spend everything from the account. And then you can imagine that, one key you would keep in a cold storage, and the other key would be your usual key. And, you can do other things. This is just an example. And then, this would be enough, for example, for a simple wallet. You would be able to deploy it. And then you could deploy other things, like I came up with identity, some information you can attach to it, or you have full flexibility in what you want to deploy, more complicated kind of accounts that you think of the regular smart contracts, for example. AMM could be something completely different. It would have different sets of components deployed in it. You could have voting accounts, and they would have different set of components deployed in them, and so on and so forth. But developers actually write these components, and then you could attach the components. And in Miden, we actually also allow mutable accounts where you can deploy them, accounts with some set of components, and then you can update them and add more components later on. And to kind of double-click it a little bit on the component. The component itself, as I mentioned, consists of a send and receive, or it consists of a set of interfaces. In the case of basic wallet, for example, it's a send and receive function. And it also defines kind of what storage requirements you have for this component. So, for example, for basic wallet, you don't have any storage requirements. There is nothing. It just sends and receives asset. It doesn't have any impact on the internal storage. But for example, you could have an ECDSA authentication component, and that component would need to store a public key of the account inside the storage. And so the storage model is actually in Miden is very flexible, where you can have different storage slots associated with different components. Those storage slots could be simple values, 256-bit value, or it could be a map. It could be like an arbitrary, like as you have a storage on Ethereum, where you have like a key value map with like 256-bit keys and 256-bit values. So you can actually define for this component, I need like two simple storage slots, and I need a map storage slot. We'll add others like array storage slots later on as well. But your component specifies what it needs. And for example, in this case, it's a single key. If you wanted a multisig, you could have like 3 keys, and the logic there would say it's 3 out of 5. And then you can have like, there is an authenticate function which would verify a signature that is done with the CDSA, but you could also rotate keys. You can do other things. I kind of put some examples here. So this is like, I think is a very powerful model, and also very, very different from like how we think about accounts usually, because there are several layers of like account abstraction itself. Actually, account becomes account plus like how nodes interact with it, but also it becomes this layer of components that allow you to like compose things in a way that is very flexible and like updatable and opens up like new possibilities, I think. But this is basically my talk. It just covers kind of how we do things in Polygon Miden. A lot of this like is very, very new, so like I'm happy to answer any questions. I think I covered a lot of new concepts, so happy to clarify. Or if no questions, then I can answer them later. So the question was, what is the strongest use case for this kind of model? I think there are really 2 use cases, and for this client-side proving. So what we want to enable this, like the reason why we did it this way, is to enable client-side proving, where you can execute transactions locally and then just send proof to the network. The first and obvious use case is privacy. Because if you can do, if you ask the network to execute things for you, then you have to tell the network what the data is and what the code is and all of that stuff, and then you don't get any privacy. So it's very similar to like, use case that Aztec is solving, where, like this is the requirement. Like you have to have client-side proving for privacy. The second and maybe less obvious use case is it actually unlocks scalability to a much higher degree than is possible with what I call transparent blockchains. Because you can think about executing, whatever you execute locally has very little bearing on how complex this is for the network to verify. ZKPs are like exponentially faster to verify as compared to like actually time it takes to execute it. So I could have like a simple transaction that does a basic transfer, and I could have a transaction that, like, I don't know, like use the data center worth of computation to run some inference model. From the network standpoint, you see almost no difference between the two. So you kind of like lift gas limits almost completely. I mean, there is some restrictions, there is some resources. You like, for example, there's a limit on how many nodes you can produce in a single transaction. But as far as computation goes, you are completely unbounded in what you can do. The other aspect of this is actually state, because I didn't talk about this much, but this allows you to put state off-chain. You don't need to put state of the account on-chain. Like it's all, like basically every account can be represented by a hash of the state of that account, and you have a proof that you generate locally that says, okay, my account transitions from state X to state Y, and therefore you don't get state bloat, or at least a much reduced state bloat, like the number of accounts, like every account is like, let's say 30, well, actually like 40 bytes, like, and so your account can have, I don't know, megabytes of data under it, but from the network standpoint, again, it doesn't really matter. There are some challenges with that. For example, if you lose your account state, you're kind of locked out of your account, and there are ways to kind of deal with that, but it does unlock the scalability where I think people frequently talk about execution as being the bottleneck, but I think state is as much of a bottleneck, if not more, usually, especially if you go to like really high scale, high throughput. Any other questions?
Hi. How does fees work? Like, I imagine the sequencer needs to know publicly how much the fees is. Does that leak how do you hide addresses being leaked then?
Yeah, so, and to be clarified, like we're still working on fee model, but basically it will look very much like a multi-dimensional fee model where there are different resources. And for example, the network knows how many nodes have been consumed in a transaction. The network knows how many nodes have been produced. So like for every consumed and produced node, you would have to pay like a fee. It's like a different resource because, you can, like there are two different resources, right? It also says, okay, for example, another thing is how many cycles did you take to execute? So like instead of gas, there is some relationship still, like it's a logarithmic relationship, but like a transaction that takes 100K cycles to execute versus 100 million cycles, you still need to do a bit more verification kind of work. So there is like a fee would be attached for like how many cycles did the transaction took to execute. There are other things like I only talked about like the private accounts, but if you have a public account, is how much data you put on network. So private account always puts only 40 bytes, but the public account actually puts whatever is like the contents of the account. So there's like 6 different resources basically, and the transaction would generate saying, okay, I'm paying this amount as a part of my transaction fee, and then when it gets included into a block, it basically checks, does it satisfy the base fee for every one of these assets, like cumulatively, and then if it does, then there is going to be a priority fee as well for prioritization. So, but it will look very much as like a multidimensional, like EIP 1559, I think. I think in terms of what it is leaking, like you do know like this transaction produced 5 nodes and consumed 5 nodes. It updated the state of the account from X to Y, but you don't actually see anything else. You don't see the destination addresses. No. All right. Well, thank you very much. And again, Julian, thank you so much for agreeing to swap with me.